Привет. Привет, Акай. Значит, я хочу кое-чего рассказать. Значит, почему я выбрал именно эту тему? Ну, потому что мне самому это было интересно. Вот. Поэтому и мало кто про это знает. Так что я даже ее включил там в свои лекции в университете по истории математики. Оказалось, что действительно никто этого не знает. Я буду говорить по-английски, чтобы не было когнитивного диссонанса. Ну, надеюсь, что так будет все здорово. Okay, so we are talking about the Archimedes lever. So a lever is a simple device. So we have this solid rod. It is put on this pivot, so it can turn around this point, and if this length, say call it L1, and this length is L2, and here we apply a vertical force, say P1, it is the gravity force, and here we apply the force P2, yeah, and if the lever is at equilibrium, then we have the following relation. P1 L1 equals P2 L2. Or we can write the same otherwise. P1 divided by P2 equals L2 divided by L1. So at equilibrium, the forces are inversely proportional to the length of corresponding pieces of the lever. So I think you have already seen this rule. It is called the Archimedes law, or Archimedes equation, or simply Archimedes lever. The problem is what it is. No, the lever itself, this device, of course, was known much earlier than Archimedes formulated this rule. I am sure that, say, the builders of Egyptian pyramids used it. It was, I think, quite necessary for their work when you have to move very heavy masses. Then you really need such device to amplify your force, because making this ratio, say, very small or very large makes this ratio very small and very large. So if say L1 is 1 and L2 is 10, then we have that P2 is tenfold. Just a minute. Sorry. Okay, let me draw it better. So it is small and this is large. Yeah, so if L2 is 10 times L1, then you can take P1 1/10 of P2 by this equation. And so we can say lift 10 kilograms applying the force of just 1 kilogram. So the question is what it is, how to look at this relation. I mean, is it experimental fact? So somebody like Archimedes himself really measured the forces and the length and found after a number of experiments that this relation holds universally. Is it experimental fact, or is it, say, a theorem which he has proved, yes, mathematically, somehow derived it from some previously known or obvious statements, or something else? And I would say that the great achievement of Archimedes was that the last is true. It is a theorem. But how could he derive it? Where he took the, say, prerequisites of it, conditions of this theorem previously? Frankly, they are taken from the common sense, and they are things which can be easily formulated as axioms, and they can be made axioms, so it is a real theorem. I would say that Archimedes is, I think, the greatest mathematician of this ancient Greece. Exactly Archimedes. Why not Euclides? Euclides was, I'm not sure that he really existed. It is the name of the author, or authors, maybe there was more than one, say, company of authors which called them together Euclides, who collected everything which was known by that time in mathematics and wrote some all-inclusive compendium which was called Elements, Euclidean Elements. Yeah? Similar things were done, say, in 20th century by other groups of mathematics who tried to do the same, but in the modern context. There were several such modern Euclides. And Archimedes was different. I would say that his way of thinking and way of writing mathematics was very modern. My impression when I read some papers of Archimedes, they fortunately were saved and we can read them. I am reading typical modern mathematician. No, simply he solved different problems. Yeah? His solutions, his way of thinking is more or less the same as the way of thinking of today's mathematicians. Yeah, and what is even more important, that he was the first applied mathematicians. So he solved the problems which were beyond the pure mathematics, no, in this case problems of statics, of mechanics, and applying the skills which he had in pure mathematics. He also solved the problems of pure mathematics. For example, he was the first to find the volume of a ball of given radius, or the area of the sphere of given radius. It was the peak of ancient mathematics. In fact, it was already a door to mathematics of modern times. So, okay, let us go to Archimedes, how he derived this property, this law. So let us start from the simplest case. Consider the lever such that here we have L1 and L2, and L1 equals L2. So equal sides. And now let us apply to these sides equal forces. P1 and P2. P1 equals P2. Now, it is clear that this system is at equilibrium. Why? No, because assume that, say, the right side is will go down. Yes, so it is out of equilibrium, so either it will tilt this way or tilt this way. So if it's tilting this way, then this is symmetric. Yes, so we can change left and right, and nothing changes. So if by some reason this point goes down, then by the same reason this opposite point will go down. Yeah. So it is one of the first instances of using symmetry for such things, but I would say not the first. There was the famous reasoning, I think, of Anaxagor, who lived about 300 years before Archimedes. Anaxagor considered the following question. That time it was not obvious that the Earth is a ball. So Earth is a ball, and why? And the ball which is surrounded by the emptiness. Yes, just a ball which hangs in empty space. The real objection was the following. Suppose that it is true, why doesn't it fall down if it has no support? Yes, it's just ball in space. Why, if you take, say, an apple like this size and let it hang in the space, it will not hang, it will fall down. Why the ball on which we are living doesn't fall down? And Anaxagor formulated the following. Okay, suppose it will fall down, but if it is hanging in this infinite space, then all directions are equivalent. Yeah. So if by some reason it should fall down, then by the same reason it should fall up, or right or left. Yes. And so there is no chosen direction to fall, and in this case it will not fall at all, because there should be some reason to fall, and the reason to fall in any direction is the same. Yeah, so this means that no fall at all will happen. Okay, so this system is at equilibrium. It is one piece of reasoning. The second piece of reasoning, if here we have the force P1 and here they have the force P2 which are equal, let me simply write that equals P and L1 and equals L2 and equals L. Then it will press on this point with the double force. With the double force 2p, and this point will press on the lever with the doubled force. So two forces applied at the end points of size p going down, and one force of the size 2p going up, and in this situation this lever is at equilibrium. Now we can get rid of this support, simply replace it by this force, double force 2p applied at the middle. So we have the following configuration. It is the lever, the solid rod. So here we have force P, here we have force P, and in the middle we have force 2P directed up. And if this is at equilibrium, then this is at equilibrium. Yeah? And now we have we can make the next substitution. Instead of this force, no, the force can be made by, say, the two masses which are suspended at the point. We can replace this force P by another support. So this is the lever. Here we have, instead of this force, we have another support. Here at the end we have the force 2P, and here we have force P. Yeah. So this is L and this is L. Yeah. Or no, if you don't like this configuration, we can overturn it and see this configuration. This is the pivot. The lever can turn around this point. Here we have force 2P, and here we have force P. And all this system is at equilibrium. So this is L, and this is 2L. But look, it is almost the configuration which I wrote it here. Simply this, we have two forces which are applied to the different points of the rod at one side of the lever. Yeah. So what can you do? You can continue this lever up to the left. Yeah. So this 2L. This is P. Continue it to the left. It is L. And apply here the force 2P. I'm sorry. It is applied here to the right. It is P. And here just a minute. Okay. Yes. This is P. And here, this force is directed down, but it is the same if you continue it here and apply the same force up. The effect will be the same by the same reasoning. Yes, 2p. It is L. It is 2L. So you have this situation that now let us direct these forces down. If here is equilibrium, if you direct down, it will be also equilibrium. So here it is L, it is 2p, and here is 2L, and it is P. And we, after these transformations, we arrived at a configuration which we just have a particular case of Archimedean situation. Here the product of force and length is 2p times L, and here times L, and here we have P times 2L, and the system is equilibrium, and of course they are equal. So in this case we proved the Archimedean law about the lever. Yeah. Now what we were doing here, in fact, we were doing something like transformation of algebraic equality or algebraic equation. Yes, so all this transformation, it is not exactly like this. No, for example, here, when you replaced the force which is directed to the down here at the distance L by the force which is directed up on the continuation of this lever by the same distance L, this is analogous to when you have equality, something, say A plus B equals C plus D, then you take A from the left side, move it to the right side with opposite sign. Yes? So you have, say, A plus B equals C. If you move A here, you have B equals C minus A. You take A and move it here. So it is what was done here. Yeah? No, I'm not sure that Archimedes thought exactly this way, but his reasoning that I read in his work was approximately like this. So we proved that if the one side of the lever is half, one side is twice other side, right side is twice left side, and right force is 1/2 of left force, then the lever is equilibrium. And conversely, if it is equilibrium with this relation of the sides, it is then you have the inverse proportionality of the forces. Yeah. So and if you look at this, it is quite surprising that we could reach this configuration using these simple but non-trivial transformations. Now, okay, what can we do further? We have just one particular case of Archimedes lever. Now we want to go further. Suppose we have the lever okay. Yeah. Consider this configuration, which we have already. It is 2p. It is p. It is L. It is 2L. Yeah. So this configuration is at equilibrium. Now you can see that on this support we have a force which is equal to sum of these forces, 3p. Yeah. And this support, this pivot, is pulling the or pushing this point of the lever, pushing up with the force 3p. Yeah. Now we can eliminate this support, simply draw this picture without support. Here we have the force 3p, here we have the force 2p, and here we have the force p. And now we can replace this force by support. Namely, we can draw this support or this pivot. So here we have the force 3p. Here we have force p. It is L. This is 2L. Yeah. But more important that this distance is 3L. Yeah. No, or to have better feeling, you have this situation. Here we have the force 3p. Here we have the force p. It is L, and this is 3L. Yeah. No, and now we can replace this force 3p, which pushes down, by the force on the continuation, which pushes up, for 3p. Here we have force p. It is L, it is 3L. Yes, because we take it on the continuation. Now let us turn it down to have more usual situation. 3p down, here a force p down, it is L, it is 3L. So, and again you have that L1 equals L, L2 equals 3L, P1 equals 3P, P2 equals P, and then P1 L1 equals 3PL, and L1 P2 L2 equals again 3PL. So the relation is proved when one side is 3 times longer than other side. Yeah. No, now we can prove the same way when one side is 4 times longer than other side, and so on, up to whenever you wish. And so this way we prove the following general situation. So if it is L, it is NL, it is P, it is NP. And then this system is at equilibrium. Yeah? No, okay. And now one more small effort. Oh my God. What happens if here we have ML and here we have NL? What happens in this case? If here you have P1 and here you have P2, how to find conditions of equilibrium? No, first of all, let us do the following. Let us suspend, apply the force P here. No, this length L. Yeah, remove it. Here we apply nothing, and so to be at equilibrium it should be M P1. Yes, and this force MP1 can be replaced by the force here. So if you take n times more, n times longer side, then here we can apply the force MP1 divided by n, and it is the equivalence of this force. Yeah. So I apply this previous result twice. First I replace this force P1. Okay. I replace this force P1. Let us take L here by P1 times M, and yes, and this force is equilibrated with the force P1 times M divided by N. Yeah. So this means that this force P1 P1 And so P1, so what is L1? L1 equals ML, L2 equals NL. And P1 L1 equals M P1L, and P2 L2 equals, so P2 equals P1M divided by N equals P1M divided by N times L2 times NL equals P1 ML. This N is cancelled. Yeah. So this means that P1 L1, sorry, P1 L1 equals P2 L2 in this case. So even when the lengths are in rational relations, so L1 L2 equals M divided by N, in this case the Archimedes law is also proved. Now what remains? Remains a small part, but which was that time beyond Archimedes' knowledge. It is how to prove it when L1 divided by L2 is not rational like M divided by N, but irrational. It is not so easy, and let me simply say that it is also true, but requires a little more thinking, maybe another half an hour, and maybe some other time. So this way we proved this theorem. I think it is really beautiful way of thinking, and let me finish this today and tonight, and then maybe we'll continue next time. For now, have a good time. Bye.